Hello everyone and welcome back to part 5 of our Metroidvania tutorial series. In this 5th installment, we'll be improving the mechanics we've already established while also introducing some exciting new features. Get ready to level up your game development skills as we explore the art of crafting intricate levels reminiscent of those in Hollow Knight, complete with a parallax effect and multiple layers. We'll also be adding scene transitions, allowing for seamless navigation between different areas. By the end of this tutorial, you should have something that looks like this. So, start up Unity, grab some coffee, and let's take our Metroidvania project to the next level. First, let's change our spell sprites' filter mode to bilinear, so they don't look pixelated. Let's then make some adjustments and improvements to the mechanics we already have. To begin, let's adjust the player's recoil Y speed to 32, allowing for more controlled and responsive movements. Let's then make the player and canvas a prefab. Next, let's streamline the casting and healing actions by assigning them to the same button. First, open the input manager and locate the button responsible for healing. We'll rename it to cast/heal to reflect its new dual functionality. We'll create a timer variable called cast or heal timer to keep track of how long the spell/heal button has been pressed. Now let's modify the spellcasting condition. Instead of checking for a button pressed directly, we'll change it to input.getButtonUp and add a check for the timer being less than or equal to 0.05. This ensures that the spell is cast when the button is released within a short time frame. For healing, we'll adjust the condition to input.getButton and add a check for the timer value being more than 0.05. This ensures that healing is activated when the button is held down for a slightly longer duration. By implementing these changes, we can simplify the gameplay mechanics, allowing the player to seamlessly cast spells or heal with a single button press. Remember to also change the button names from cast spell and healing to cast/heal. Then reset the cast or heal timer when the cast/heal button is not being pressed. To avoid the grounded method being set to true when the player hits the side of the ground platform, we'll make adjustments to ground check X value by setting it to 0.4 in the inspector. To improve the jump method, we'll remove the jump code from the p-state is not jumping if statement and only add p-state is not jumping to the ground jump code. Then we'll remove the else from the air jump code. In order to refine the jump cancel method, we'll remove the condition p-state.jumping and rb.velocity is more than 0. Instead, we'll replace them with rb.velocity is more than 3. This alteration will provide better responsiveness for our jumps. Next, let's go to our Bloodspurt particle system and open the editor. Let's reshape the size of the lifetime curve so that our particle decreases over time instead of increasing over time. Let's then set the velocity over lifetime linear to curve and set the X curve and Y curve to these shapes. Then set the speed modifier curve in the same section and set the curve to this shape. Additionally, we'll make a crucial change to the enemy base class. Instead of utilizing the awake function, we'll switch it to the start function. By making this adjustment, we ensure that the enemy behavior is properly initialized at the right moment. Remember to make this change for the subclasses as well. This isn't strictly necessary, but I found that it helps preventing bugs from happening in the future. Let's then set our dash direction to be based on p-state.looking right instead of based on local scale. And finally, let's fix our singleton. Currently, our singleton doesn't carry over to the next scene. First, go to our player singleton and instead of destroying this, destroy game object. Then add don't destroy unload at the bottom of the awake function. And with those improvements in place, we're ready to dive into the heart of this video. In this section, we'll explore the fascinating world of parallax and learn how you can create stunning scenes with multiple layers, just like the enchanting environments of Hollow Knight. Now, before we dive into this section, I want to emphasize that level design is a creative process that allows for your own inputs and ideas. While I'll be demonstrating specific techniques and concepts, it's essential to understand that flexibility and personalization are key. So focus on learning the concepts and tricks that I'll be sharing, rather than strictly following this part of the tutorial. Parallax is a key technique used in game development to add depth and visual interest to 2D environments. It involves layering multiple images or elements at different distances from the camera, creating an illusion of depth and movement as the player navigates through the scene. I'll be using the 2D Dark Cave asset pack from itch.io. Link is in the description below. Now let's dive right in. First, rename the current scene to cave_1 for clarity and organization. Secondly, open up your asset pack and adjust the sprite settings by setting the pixels per unit to 32, the mode to multiple, the maximum size to 4096, and the compression to none. This ensures optimal quality and performance. Thirdly, utilize the automatic slice feature to cut up the sprite sheets into individual usable sprites. This simplifies the process of working with sprites in your scene. Step 4. Create 3 sorting layers in the sprite renderer called background, midground, and foreground, and make sure they are in the right order. This allows us to organize and control the visual stacking order of our game objects. Step 5. It's time to set up the game objects for our parallax layers. Create 3 new game objects named background, midground, and foreground respectively. Step 6. Within each of these 3 game objects, create 3 child game objects. Give them names based on their parents' game object names, adding an _0, _1, and _2 at the end. For example, we'll rename the child game objects under background to background _0, background _1, and background _2. Step 7. Adjust the Z position of the child game objects to create the desired depth effect. Set background _0 to a Z position of 5, background _1 to 10, background _2 to 15. For midground 0, let's set it to 0.5, midground 1 to 0, and midground 2 to negative 0.5. Finally, foreground 0 should be -2, foreground 1 should be -4, and foreground 2 should be -6. These distinct layers will serve as our canvas for building a rich sense of depth, similar to what we find in Hollow Knight. And now, without further delay, it's time to unleash your creativity and start constructing your captivating parallax scene in Unity. First, let's start by using the Floyd sprites for our floor. We'll attach these sprites to the midground 1 game object, set their sorting layer to midground, and set their order in layer to 0. We'll then set the layer to ground and add a box collider that fits within the sprite. To create the entire length of the floor, we'll duplicate these sprites. For some variation, we can also use the floor 9 sprites. Now, if you look closely, you'll notice some gaps between the floor tiles. To make them look better, let's make a few adjustments. Head over to our camera settings and change the background type under environment from skybox to solid color. Then set the background color to black. This will help us in creating a more cohesive look by blending the bottoms of our floor to the background. To fill in the gaps and add some detail, well, let's add some rocks and select stalagmites. Stalagmites, okay. We'll place these elements in front of the gaps between our floor tiles. We can attach them to the midground 2 object and duplicate them to add more detail to the scene. Be sure to adjust the sorting layer of these elements accordingly. Now when we hit the play button, you should see a continuous cave floor. For the walls, we'll use long vertical floor sprites. As for the gaps, we'll use shorter vertical floor tiles to fill those in. Set the sorting layer of these gap fillers to midground -1 and the main wall tiles to midground 0. We'll also follow the same process for the ceiling using the floor tiles that face downwards. Let's not forget about the foreground. We'll add rocks, stalagmites, and stalactites to the foreground layers. Adjust their sorting layers accordingly as well. To enhance the depth of field effect, I personally like to darken the color of these foreground elements, making sure that they don't distract the player, and make it evident that these are foreground elements. Moving on to the background, we'll create a large rock column using the vertical floor sprites. The sides of the column will be made using these sprites as well, and in the center we'll place the black square included in the sprite pack. To organize this, create a parent object named column and attach it to the background 2. Set the sprites to the background sorting layer. Make sure to reset the Z position of the column and its sprites to match the background 2 layer. To simulate the depth of field in the background, we'll add fog to each background layer. Create a child square sprite under each background layer and expand them to cover the entire scene. Set the alpha of these squares to 77 for each. Adjust the sorting layer to background and ensure that their order number in the sorting layer is higher than the background layer. This will create a blurred effect, with the background becoming foggier and blurrier the further you go back into the scene. I'll also be adding some platforms into the scene to give the level some variety. Take some of the platform sprites from the platform sprite sheet and add a box collider and adjust it to fit the sprite, then set it to ground layer. The asset pack also comes with some animated plants that we can use to create some foliage for our scene. Go to vegetation and set the pixels per unit to 32 and increase their maximum size to 4096. Select the none for compression, and basically these settings are the same as our cave sprite asset pack settings. Next, we'll create game objects for each of the vegetation types and create an animation for them using the sprites for each of the plants given in order. Save these animations to the animation folder. Once that's done, make sure these animations are looped, and once that's done, create a folder in prefabs called plants and save these plants to the folder to make them prefabs so that we can reuse them whenever we need to. Spread them around the level at different layers to bring your level to life while using concepts we taught above like darkening foreground elements to create a more realistic depth of field effect. I'll also be making two other scenes called Cave_2 and Cave_3. Cave 2 will be a long horizontal room that will feature platforming challenges and a shortcut at the top of the room for them to return to the starting point. Cave 3 will be an upside down capital T with a vertical platforming section leading to two rooms at the bottom. Remember to add the player and the canvas to these scenes as well. I'll use the same process and concepts as in Cave_1.
Amogus.
Once you've done building these two scenes, go to Edit, Build Settings, and open each scene up and add them to your build. This ensures that they'll work for our next feature, Scene Transitions. First, create a game object called Scene Transition with a box collider and make this box collider a trigger. Then add a child empty game object called Start Point. The trigger collider will start the scene transition, while the start point will be the point at which the player starts the scene in. This is done so that we can have multiple entrances and exits to a scene. Let's create the scene transition script on our game object. We'll have 4 private variables: a string variable called transition2 representing the scene to transition to, a transform variable called start point representing the player's entry point in the scene, a vector2 variable called exit direction representing the direction for which the player is exiting, and a float variable called exit time representing the amount of time it takes for our player to exit the scene transition. Make sure to mark these variables as serializable. In our onTriggerEnter2D function, we'll check if the entering object is the player. If it is, we'll load the next scene using UnityEngine.SceneManagement.loadScene transition2. To ensure that the player starts at the designated entry point when entering a scene, create an object called Game Manager and create a script called Game Manager on it. Then make the Game Manager a singleton, like for our player. Add a public string variable called transitionedFromScene to store the previous scene. This reference will help us determine the appropriate start point when entering a scene with multiple scene transitions in that particular scene. In the starts function of our scene transition script, check if the transition2 variable matches the transitionedFromScene variable. This way we can identify the correct starting point for the scene transition based on the scene we came from. If true, set the player instance's position to the start point position. Set the transitionedFromScene variable to the active scene on TriggerEnter before loading a new scene. Let's go back to Cave 1. I'll create a hole on the left wall for our scene transition. Let's then assign all the proper variables, set transition2 to Cave 2, and set the exit direction as 1 since the player walks to the right when exiting the scene transition. Finally, set the exit time to 0.25. Now, if we play, we should have a smooth scene transition from one scene to the next. Make the scene transition a prefab so that we can add these to the other scenes later. back to the player controller script and add a public coroutine called walk into new scene and pass two arguments, a vector to exit dir and a float delay. Then add a new public bool to our player state list called cutscene and set its default value to false. Checks if the x component of exit dir vector is not equal to 0, indicating horizontal movement. If true, the x-axis variable is set to 1. If true, the x-axis variable is set to 1 if exitdir.x is greater than 0, or it is set to -1 if exitdir.x is less than 0. This determines the direction in which the player should move. Then the move function is called to handle the player's movement based on the x-axis. The flip function then flips the player in the corrected direction. We then wait for the delay amount of seconds to let the mini cutscene play. Then we end the cutscene by setting pstate.cutscene is false. Then go back to our scene transition script and set the cutscene player state to true before the new scene is loaded. Finally, go to our player controllers update and fixed update functions and add a pstate.cutscene return at the top. This stops our other functions from interrupting our cutscene. We'll call the coroutine in our scene transition script by adding start coroutine, player.instance.walkIntoNewScene, exit direction, and exit time. We'll add this in the start function of our scene transition code and inside the if statement and under the startPoint.position line of code. Let's go back to Cave 2 and add a scene transition on the right wall. We'll set the x to -1 for our exit direction as we want to exit straight towards the left. Set the transition to variable to Cave 1. And now if we try out the scene transition, we should have a nice walking cutscene as the player walks out of the scene transition. We can also have a vertical scene transition. Let's create a hole and a scene transition to Cave 3. We'll then set the exit direction to -1, 1. This is so that the player will jump out of the scene transition at a diagonal and jump up and out of the hole. Here's a graph showing the directional vector and why I set the exit direction to -1, 1. As you can see, the line is going towards the left corner and in the direction we want our player to exit out of. Let's also set the exit time as 0.5 so our player has enough time to jump out of the scene transition hole. Let's then add a scene transition in Cave 3 back to Cave 1. We can leave the variables as 0 here since the player is simply falling out of the scene transition, so no cutscene is required. And now if we test the scene transition out, we should have a smooth scene transition with the player jumping out. I also like to rename the scene transitions according to what the scene they're transitioning to, just to make it easier to keep track of. For example, I'll rename the scene transition to Cave 2 to Cave 2 Transition. Next, let's add a fade to black as we transition between scenes and a fade out when we enter a scene. Let's start by creating a script called UI Manager in our canvas object and make it a singleton. First, we'll create an image on our canvas and move it to the bottom of the canvas children so that it will be rendered on top of the other canvas elements. Next, let's change the color of the image to black and stretch the image to fill. Next, rename this image object to Scene Fader and create a script called Scene Fader on the game object. In the Scene Fader script, declare that we'll be using the Unity.UI library. Then create a serializable private float variable called FadeTime and add a private image variable called FadeOutUIImage. Next, set FadeOutUIImage to image component of the Scene Fader game object in the awake function. Next, create a public enum called Fade Direction. In Unity, an enum is a data type that defines a set of named values, representing a fixed list of options or states. Enums are commonly used to define and organize discrete values, such as different game states, player actions, or specific types of objects. By using enums, you can improve code readability and maintainability by referring to these named values, instead of using arbitrary numbers or strings. In this case, we'll be using an enum to keep track of whether we want to fade our image in or out. Next, create a private method called setColorImage and pass in a ref_float alpha argument and a fade direction argument. The ref keyword will allow us to read and modify the value of the argument. In the function, type fadeOutUIImage.color equals new color fadeOutUIImage.color_r fadeOutUIImage.color_g and fadeOutUIImage.color.b alpha. Alpha plus equals time.delta time times 1 divided by image fade time times, if fade direction is fade direction out, then -1, else 1. The first line sets the color of the UI image, keeping the existing red, green and blue RGB values unchanged, but updating the alpha value with alpha. This is done to adjust the transparency value of the image. The following line is responsible for modifying the alpha value over time. It uses time.delta time to ensure a consistent speed across the different frame rates. The value of alpha is increased or decreased based on the fade direction variable, which represents the desired fade direction, either subtracting or adding to the current alpha value. Next, create a public I enumerator called fade and pass a fade direction argument into it called fade direction. In fade, add two local variables called alpha and fade end value. Using a ternary conditional operator, set alpha to 1 and fade end value to 0 if fade direction is equal to fade direction.out. Else set the alpha to 0 and fade end value to 1. Next, type if fade direction is equal to fade direction out, while alpha is more than or equal to a fade end value. Set color image ref alpha, fade direction, yield return null. Then fade out UIImage.enabled equals false. Else fade out UIImage.enabled is true, while alpha is less than or equal to fade end value. Set color image ref alpha, fade direction, yield return null. This controls the fade effect based on the value of the fade direction variable. If the fade direction variable is set to fade direction.out, once the fade is complete, the fade out UI image is disabled. If fade direction is not fade direction.out, indicating a fade in effect, the fade out UI image is enabled. The code then enters a while loop and increases the alpha value until it reaches the fade end value. Similar to the previous case, the setColorImage function is called to update the image's color. In both cases, the yield return null statement allows for smooth animation by yielding control back to the Unity engine before the next iteration. Finally, create a public I enumerator called fade and load scene, and create a fade direction parameter and a string scene to load parameter. In this coroutine, type fadeOutUIImage.enabled is true, you return fade direction. SceneManager.load scene to load. This fades the black image in and loads the scene we want to load. Go to our UI Manager script and create a public scene fader variable called scene fader and set it in start to get component in children scene fader to get a reference to our scene fader script. Now go back to our scene transition script and add start coroutine UIManager.instance.scenefader.fade scenefader.fade direction out to get the scene fader to fade out every time a scene starts. Next, replace the SceneManager.load scene line with start coroutine UIManager.instance.scenefader.fade and load scene scenefader.direction.in transition 2. Now that our scene fader coroutine has been called, let's go back to our Unity editor and test out the fading. Looks great! Now let's get some lighting in our scene to improve the aesthetic of our scene. First, we want to create global 2D light by right-clicking the hierarchy and clicking Create, Lights, then click Global Light 2D. Wait, where are the 2D lights? What? They're in URP now? But there was no announcement. The documentation is still the same. What? Oh, god damn it, you're not there!
Oh, do it again.
In life, sometimes we run into unexpected problems that occur in our modern societies. But with modern problems comes modern solutions, and we must improvise, adapt, and overcome these challenges. So to get 2D lights into our project, we'll have to switch our render pipeline over to the Universal Rendering Pipeline or URP. To do this, we'll first need to install the URP package from the Unity registry in our package manager. After the package installation is complete, close the package manager window. Right-click on the project tab and select Create, Rendering, URP Asset 2D Renderer. In your Unity project, navigate to Edit and then Project Settings. In Project Settings, find and select Graphics. Under Scriptable Render Pipeline Settings, click on the Custom drop-down menu and choose Universal Render Pipeline Asset. Next, create a new material and set it to the URP Sprite Lit default material. Then search for all sprite renderers in your scene by typing T:sprite renderer. Highlight all the game objects you find and replace their sprite materials with the new one you've just created. Remember to also change the sprite material of your prefabs. With this done, we should now have 2D lights in our scene. To start, we'll first need to add Global Light 2D to establish the lighting of our scene. We'll want our lighting to be dark, seeing as we're in a cave, but not too dark as we want the player to be able to clearly see the game. Next, we want to add a spotlight to our scene transition prefab and enlarge it and extend it to make it noticeable for the player so that they know that there is a scene transition in the area of the spotlight. Finally, let's add some freeform lights in our Cave 1 scene to make it look like there is some light coming from the cracks in the ceiling. Freeform lights are especially useful as you can control the shape of the light source, which allows for some dynamic and greatly lit scenes. For the sake of the length of the video, I'll just be making sure that Cave 2 and Cave 3 are lit up well with global lighting. Feel free to further adjust and add to the lighting in these scenes. When transitioning to URP, we encounter an issue where the invincibility flashing no longer works due to the sprite material color not changing. To address this, we'll implement a solution. First, we'll introduce a private bool variable called canFlash and a coroutine named Flash in our player controller script. Within the Flash coroutine, we'll toggle the sprite renderer's visibility using sr.enabled equals not sr.enabled, followed by setting canFlash to false, waiting for 0.05 seconds with u return new wait for seconds 0.05f, and finally setting canFlash back to true. This will cause the player to disappear and reappear after the specified duration. Next, we'll modify the flash while invincible method. If the player is invincible, pState.invincible, and the timescale is above 0.2, we'll check if canFlash is true and initiate flash coroutine using start coroutine flash. Otherwise, we'll ensure that the sprite renderer is always enabled. sr.enabled is true. By incorporating the timescale condition, we ensure that the player starts flashing only when the timescale is relatively high, preventing frustration and difficulty in locating the player on screen during moments of low timescale. Now if we test this out, we should have a player that flashes in and out when the player gets hit. And that will do it for part 5. In the next part, we'll continue to improve on the presentation of our game by upgrading our camera to one that has all the features of Hollow Knight's camera. We'll also be adding a flying ranged enemy and an enemy that charges at you when it sees you. We'll also be adding in platforming challenges like spikes into the game. Thanks for watching, and we'll see you in the next video. Hey there! Want to support what we do? You can help us by becoming a patron. This will give you access to the project files for our tutorials as well as patron exclusive posts on our blog. Any support you give will be invaluable to us, as currently we're only making back about 20 cents for every dollar we put into content creation. Your patronage will go a long way to help us make this a sustainable endeavor. See you in the next video!